Good morning, everyone, and welcome to today's lecture on Python for data visualization. My name is Chris Myers. I'm in the Cornell Center for Advanced Computing. And as was noted on the previous slide, if you have questions during this talk at any time, please post them in the chat. My colleague, Ben Trumbor, will be helping me, will be assisting me in moderating those questions. So with that, let's get started. I'm going to describe at least some of the important components of the Python ecosystem for data visualization, sort of spending most of the time talking about sort of how to generate figures and plots for things that you might put into papers or presentations, and then also about how to use tools for interactive data visualizations and sort of building up web servers that support that. I'll talk a little bit at the end about 3D rendering tools and tools for domain-specific applications. And just a word about the slides. So this talk is actually being given in a live Jupyter notebook running in Jupyter Lab, and I'm using organized this into separate slides for presentation. I previously used the Rise package for this, but that's no longer sort of working with the newer Jupyter Lab. So I'm experimenting with a new tool for doing the slide presentation. So bear with me, the user interface is a little bit different, but hopefully everything will flow smoothly enough. So Python is a programming language first and foremost, and then on top of that, it is an ecosystem of lots of useful tools and packages that have been developed by many people over the years. It's a general purpose programming language, so it wasn't intended specifically for scientific computing or data science or visualization. So most of the functionality that's useful for these activities are in third-party packages and libraries. But since it's interpreted, it's a great environment for doing exploratory data analysis and data visualization. I'm just gonna turn this on. Maybe I'll be forward a little more if I turn that light on. Okay. So the focus here is on packages that have a Python application programming interface so that you can use the Python language to craft custom data visualizations. And so you would typically use these packages in conjunction with other things in the ecosystem that manage and process the data, such as pandas and NumPy and SciPy and a variety of other tools. Some packages will create a graphical user interface, a GUI, using Python to sort of drive and create data visualizations, and then sometimes provide some scripting support underneath to let you write some Python. I've shown a picture like this in previous talks. In my previous lecture, I focused on sort of this scientific computing and data analysis part of the ecosystem, and I'll be focusing today on this data visualization part of this whole ecosystem, which again is a coordinated set of tools that kind of build from the bottom up to support a variety of different kinds of workflows. If you think about data visualization, there really are many different axes on which one can try to categorize things. Perhaps first and foremost is the intended message of what it is you're trying to convey when you visualize data. And if you want to hear more about that, I would refer you to the recent talk that Ben gave in this series on creating the best visualizations for your data. I can be focused more on the mechanics of doing things within Python today, but even within that context, there's many different forms and structures of data. Data comes in many different dimensionalities, which we might need to sort of represent in different ways. There are, of course, many different types of graphical representations of sort of glyphs and other kind of formats that we can use. There are different use cases and sort of interaction modes. And I'm going to offer one slice through these many axes today. As I said, I'll start by talking about sort of generating mostly static 2D images, although that may often come from some higher dimensional data set that we want to try to represent in some approximate way. And this part of the talk will focus a lot on Matplotlib, which is a very important package, and then various packages that sit on top of that and use Matplotlib for their plotting. Then I'll pivot and I'll talk some about interactive data visualizations and some tools such as Bokeh Plotly that let us sort of interrogate data in an interactive way. And then, as I said, I'll say a little bit at the end about some other things. It's important to note, I'm not considering image processing software here. I mean, what I'm talking about is taking data that we have either from experiments or from a simulation or something and visualizing that, whereas image processing is in some sense the opposite. It goes in the opposite direction. It takes some image and then we want to apply some analysis to that to extract features from it. But again, that's really a separate topic in its own right. So let me start with Matplotlib, which, as I say, is the cornerstone of much of the Python plotting universe. It's been around for a long time and has been improved by many people, worked on by many people. And it provides really two different APIs that can be kind of interwoven. One is this more object-oriented interface which is called the axes interface, in which we create figures and axes and then can call methods on those objects. And then there's a more kind of a more imperative and functional PyPlot interface that in some ways is similar to the plotting interface that is provided in MATLAB. So this PyPlot interface is sometimes easier for very simple things and for interactive work, but the axes interface gives you more fine-grained control of plots if you really want to customize things in detail. And in addition to using Matplotlib directly, which many people do, there are these other packages in the ecosystem that use it internally for making plots and present their own APIs. And I'll show some examples of what that looks like. And one of the nice things about that is that even though they're using Matplotlib underneath, most of these packages will expose the low-level Matplotlib interface alongside with this higher-level, package-specific API, and these things can be kind of mixed and matched in useful ways. So let me just start with a simple example. Here's some Python code. I'm going to import matplotlib.pyplot as PLT, and this PLT is a conventional shorthand name. You can certainly see why we'd want to have a shorter thing, not to have to type every time. I'm also going to import NumPy, create a little data set in NumPy, and then I will plot this thing by calling the plot method on this PLT interface. So I'm plotting Y versus X, and then I can add some labels if I want on the axes. And this is sort of a default representation, but I can, for example, add sort of change the way this is represented by adding an optional format string. So if I want to plot this in red, instead I can add a format string just with an R. If I want to do this with red dashed lines, I can change that format string a little bit more. If I want to plot it also with some circles to represent the data points, I can amend the string as such. So again, very easy. We can do this interactively, sort of build up the representation that you want, and then proceed. I can make the same plot with this axis interface. So now I create a figure in an axis object, and then instead of calling functions directly from the plot interface, I call methods on the axis object, and the API looks a little bit different, but the same functionality is there. It's a slightly different set of calls that one needs to make. So my Jupyter notebook is sort of doing double duty here. It's allowing me to present this talk, but it's also rendering the plots that I'm making. And so I just want to show you that it's not, you don't have to do this all in Jupyter. You can be doing this in a terminal. You could be, for example, running the IPython interpreter. And so I've made a simple Python program here that just contains pretty much what I had in one of the previous examples. And now when I run this, I get a plot, and in IPython, rather than having it render in the window directly, it creates a separate window with this figure in it. I also don't need to do any of this interactively. I can, for example, write a program in Python that just generates the figure, but doesn't actually ever display it for me within my session. And so one way to do this is to use this ag backend. So Matplotlib has many different backends that can render things in different ways in different environments. And the ag backend is used for non-interactive plot generation. So what this is going to do is it's going to turn on this ag backend and then generate this plot and then save it to a PNG file, and I can just run this and it gets generated, and then I can, for example, open up my PNG file and see that the same figure is created. So if you're running big simulations and you want to generate figures, you're not necessarily going to be doing that interactively. You can generate things from your data using a mechanism like this. Okay, so I'm going to go back to my notebook now. And again, I just wanted to show you that it's not all tied to working in Jupyter notebooks. I can create figures with multiple subplots. So this will, for example, this plt.subplots 1, 2 will generate something, a figure with two axes, 1 row and 2 columns. And then I can, for example, create a second data set and plot that. So now I have 2 axes, which are actually indexed. It's actually a NumPy array. Whatever subplot geometry I create, I get a NumPy array of the same shape. And so ax subscripting 0 refers to the first of these on the left, and ax 1 is the second on the right. And I can plot different things in both of these different axes here and show them together. That should be run, right? I can create other, not just line plots, but often we make scatter plots with data. So for example, I can create data sets of points x and y, which are normally distributed random points, x with a mean 0 and standard deviation 1, y with a mean 0 and standard deviation 2, and then I can make a scatter plot of x versus y, and I can see what this point cloud looks like. But I can also layer additional information on top of this. So for example, I might want to compute how far each of these points is from the origin at 0, 0. So I create an array which is using NumPy, which is this distance array, square root of x squared plus y squared. And now I can use that to color. I can pass in the color is, in fact, this distance array, and I'm mapping this through a heat map, in this case, a red heat map, so that the points that are closer to the origin are darker red, and those that are farther away are lighter. And so again, we can layer additional kinds of information on top of the basic plots using options in these various kinds of commands. There's support for kind of statistical summaries like histograms. So I can, for example, I can make a histogram for both my X and my Y data, and I can see that the one has a bigger variance than the other. In this case, I'm calling a hist method in Matplotlib on the axis object, but it's actually calling the NumPy hist function underneath. So it's not re-implementing the details of how to compute a histogram, but it's using NumPy, which is really a very basic kind of numerical library for use in Python. And I can control other things too. So for example, I want to be able to see both of these things even though they're overlapping, so I can specify an opacity or an alpha value less than 1 in order to be able to see the two distributions distinctly from each other. There are other kinds of supports other kinds of plot types. I mean, there's lots of different kinds of plot types, pretty much everything that one would encounter. This is an example adapted from the Matplotlib documentation, where I've now created an array Z that lives on a grid in X and Y, and I can either show that Z array directly by mapping it with this imshow, show the image in this blues color map, or I can, for example, use a contour function to contour it into a set of discrete levels, and that's what's shown on the right there. So again, there's a lot of depending on what you want to convey, there's a lot of ability to sort of customize in different directions. Oh, sorry, I went too far there. Right. So that was just a really quick introduction to Matplotlib, and it's got lots more functionality, and I encourage you, if you're plotting things in Python, to start there and see what it's able to do. And what I'm pivoting to now is going to talk a little bit about some of these other packages that use Matplotlib for visualization, basically by building on top of that, making calls to Matplotlib under the covers. But for example, pandas, which defines various plot methods on data frames, seaborn, which provides a lot of support for visualizing and characterizing different statistical distributions and data relationships, and then others for example, network X and stats models that sort of deal with networks and statistical modeling and use Matplotlib underneath. And then finally, I'll mention briefly plotnine, which is built on the ggplot ggplot2 library that's originally from R. So again, many of the, as I mentioned before, many of these are built to support both this kind of package specific API as well as kind of low level Matplotlib customization. So here is pandas. I'm not gonna. This is some Python and pandas code that sort of reads in and oh, sorry, I went too far there. That reads in a data set on baseball statistics, and in particular batting statistics in the history of Major League Baseball. And I showed some of this during my last talk, and we won't go through the code there because that's not the point of this. But what I have now is a pandas data frame, which is a big tabular collection of data with columns, named columns, and then a series of rows. So what this particular data frame is representing is the total number of games, at bats, runs, hits, doubles, et cetera, for every year since the start of Major League Baseball. And once I have this data in this data frame, I can plot it in various ways. So for example, so now this data frame is this batting per at bat by year, and data frames have a plot method on them. And so I can call this plot method and say, I want to plot the year on the x-axis, and then I want to have separate line plots for home runs and strikeouts. And it's calling the Matplotlib plot routine underneath, but it's sort of giving a higher level interface to that. I'm not having to tell it to make a legend or anything. You can see what let me rerun this. Let me comment out these 3 lines here. I meant to do that, but I didn't. So if I just call the plot method by itself, then I get year ID on the x-axis, and then I don't get anything on the y-axis, but I do have the legend. And I think, well, maybe I want to tweak that. But what this pandas plot method has returned for me is one of these Matplotlib axis objects. And so I can call additional methods on those directly to do some further customization. And so I can give it a title, and I can relabel the X and Y labels. And again, these are now Matplotlib calls working in conjunction with the pandas plot. And it's often very useful to sort of interleave these kinds of calls like this. That was a plot method. There's a plot.bar method on data frames, which will do a bar plot instead of a line plot. And what I can do here, for example, is say, I want to look at 6 different outcomes, 1 base hits, 2 base, 3 base hits, home runs, strikeouts, and walks based on balls. And then I can basically do a stacked bar plot, which is by passing in this. So as a function of, on the x-axis, the year, I want to do a stacked bar plot of these 6 different hit types. And it works out all the logic underneath with Matplotlib, but does a very quick job of summarizing that. And now I can look at this and kind of see how the different hit types have changed in baseball over time. Seaborn is another package that uses Matplotlib underneath. And as I said, it provides kind of a high-level interface for conveying statistical information. And typically what we do is import Seaborn as SNS. And so, for example, I can take this baseball batting data and call this function, this pair plot function, and it's going to take a few seconds to run. But what it eventually now generates is for each of these 6 different hit types that I was interested in, it creates this big pair grid of plots. So on the diagonal are the distributions over time for each of the different hit types, 1 base hits, 2 base hits, et cetera. And I'm able to color these things by the decade. So one of the things that I put into the data frame was what decade each of these years was from. And so now we can see a progression from older times in lighter blues to darker, to more recent times in darker blues. And I can see how, for example, doubles have become more prevalent over over time, and triples become less prevalent. And then in the off-diagonal elements, I can see a scatter plot of the relationships between these things. So, for example, if I want to see how strongly correlated home runs and strikeouts are, I can see that in the scatter plot, and I can also see how, for example, each of them have increased in time by looking at the hue. So with just a little bit of information here, or a little bit of input, I can get a really rich summary of a lot of the data that's in my data set, and that then might sort of suggest other kinds of things. I'm sorry if you can hear a loud drilling noise outside. They're destroying the baseball field that's outside of my office, and the construction people are making lots of noise, but that's hopefully not impacting your listening experience too much. So this is a very detailed summary in that I'm doing all these scatter plots. I might want to create a slightly simplified summary by, for example, looking at just the correlations between each of those types. So the data frame has as attached to it a core method, and then the seaborn package has a heat map method. And so I can, for example, just summarize all those positive and negative correlations between the 6 different batting types by first computing the correlation and then passing that through the heat map, and representing those values. They get mapped on this heat map as indicated on the right. And I can customize that. I can say, so anode equals true means that I'm requesting that the numbers be put in the boxes there. That's what that's doing there. So I mentioned plotnine. Plotnine is a Python implementation of the functionality that's provided by ggplot2, which is a widely used R package, and it's in fact a plotting package that implements what's called the grammar of graphics. So this is kind of a whole language, if you will, that's been invented and was originally developed in the context of R and has been kind of ported to Python. It uses Matplotlib underneath for plotting, but unlike some of those other packages, it doesn't seem to as easily expose the low-level Matplotlib API for customization. That at least in plotnine, the grammar of graphics is the way you're supposed to generate plots, and it doesn't make much sense to try to step outside of that and to do things using the low-level Matplotlib API. So it presents a rather different conceptual model than most of the other Python plotting packages, and it's somewhat un-Pythonic in my opinion in its design and interface, but maybe that's not surprising. So if you already know ggplot2, or if you really want to learn the grammar of graphics, then you should certainly check out plotnine. I don't know that it's the first thing that I would go to if I were trying to plot something, if I didn't already understand what that grammar was about. But I'll show you a little bit about what it can do. So here's a data set that's part of the sort of the plotnine. Sorry, is there a question?
No, I think that was just a little spurious noise.
Okay. It's hard to hear over the drilling out here too. So within plotnine, there's a data set for different cars and some of their different makes and models of cars and their engine characteristics and other characteristics. And this is a standard kind of data set that often gets presented in data science kinds of applications. And what plotnine does is define this language, this grammar by which I can add additional different elements. So I can say I want to represent these as a scatter plot. So it's sort of this geom point function carries that information. It lets me add in a fit, actually a statistical straight line fit to the data to smooth that. And then it lets me sort of separate out into 3 different facets how many gears there are in the car. So I can sort of separate things out, and I can, for example, say I also want to color by the gear, color differently by the gear. I can, for example, add an additional entry to this top line. I can say I also want to use the marker size to represent the displacement of the engine. So this is the I guess the volumetric displacement, by the pistons in the engine. And again, that's just a quick thing that I can add that overlays additional information. You can see at the bottom, this thing actually returned this ggplot object, which is its own internal representation for how all this stuff is bundled. And again, accessing sort of low-level Matplotlib information from that is not as straightforward as in some of these other cases. So I'm done now talking about sort of the static 2D plots and things, and so I guess I could pause just quickly to see if there are any questions about any of that, because I'm going to be leaving the Matplotlib universe and moving into some other things. So if you have questions, please feel free to put them in the chat. Otherwise, I'll proceed with this next section on interactive data visualization.
No questions have been asked yet, but I'll interrupt you.
Okay, thank you very much. Okay, so again, that was for what I was describing was a little bit about how to create static figures, a figure you put in a paper, you put in a talk, whatever. But there are different tools that provide a much more interactive experience in working with data. And there are different modalities for this. One is to sort of allow greater interactive exploration, even of static data, of data that's not, you plot but you want to explore different aspects of it. But also a different modality where you can sort of run servers that can process or plot different data based on user interactions. And most of these tools are done within a web browser, so that it can use JavaScript and HTML as browser-based visuals, sort of rendering engines under the cover, but that allow you to sort of use high-level Python APIs to customize different visualization pipelines. And one of the nice things about these is you can sort of use these tools both for your individual desktop use, if you're just trying to explore data and you want to have this functionality, or to be able to serve up, say, even remotely on a web server or on some dashboard, a big collection of tools that allow others to explore data. So Bokeh and Plotly are two prominent and widely used frameworks, and I'll mostly be describing Bokeh here, but I'll talk a little bit about Plotly, and we'll note that sort of analogous functionality exists within Plotly and Dash, which support these kind of server-based operations. So Bokeh is a package really in two parts. There is the Bokeh library itself, which is written in Python, and then the Bokeh.js package underneath that actually runs in the browser. So that's actually running JavaScript, which is sort of what most browsers are talking. And what Bokeh allows one to do is write Python code to generate a visualization. This actually then automatically generates JSON objects that are passed through to the browser and then rendered, and they're potentially with different kinds of backends. And these two processes can be on different machines. I mean, I could be running my browser on my local desktop, but I could be running the Bokeh server potentially somewhere else. And because these two pieces are decoupled, the same architecture supports APIs in other languages. So even though the main Bokeh library is written in Python, others have developed user front ends in R and Scala and Julia and other languages and as long as they can write the same compatible JSON objects, then they can use the same Bokeh.js backend. And so let me show kind of a simple plot in Bokeh. So the look and feel is kind of similar to Matplotlib. I mean, I do some imports. I create a figure, and then on the figure, there are methods defined on the figure. So here's just a very simple data set with 5 XY data points, and I can call a circle method and a line method, and then I'm going to output the file to the figure to an HTML file. And so when I run this, you should see that I popped to a different tab in my browser, and in fact, I'm looking at this HTML file. So this is an HTML file that's been generated by Bokeh, which is being rendered in my browser, but it's something that I can interact with. I can move it around, I can zoom in on things, I can reset, and that's because all of the elements of user interaction are encoded in the HTML that's producing this thing. I can even, if I want, download this figure And then when I do that, I see that I've got this PNG file that's been created. So certainly being able to generate, and I could take this HTML code that is produced and stick it in a web page, a separate web page, if that was something that I was interested in. I can do the same thing, however, I can make the same plot to a Jupyter notebook cell. So I'll be doing that for the rest of the demonstration here. And again, now I sort of say I want to output to a notebook instead, but I can make the same plot. I don't tell it to save to a file. I just tell it I want to run it. And then you can see that it's successfully loaded Bokeh.js, the back end, and now I have this sort of HTML embedded figure in my notebook that I can interact with. One of the things that Bokeh, sort of a central part of it, is it creates a new data type called a column data source, which is sort of like a pandas data frame, in that it's got named columns that contain different types of data. So Bokeh has its own slightly different version of the car data set that we looked at before. And so that's what's shown here in this data frame. And now, for example, I can create a figure and create a column data source just directly derived from this data frame. And now what this allows me to do is to sort of, I can plot different rows and column, or different things on the X and the Y axis by just referring to the names of the columns. And again, I can set sizes and colors and alpha values sort of in the same way that I was able to do in Matplotlib. And so this is a plot of the miles per gallon for each of the cars in this data set versus the weight. And so just doing that isn't so special, because I could do that in Matplotlib or in pandas. But one of the things that's nice about Bokeh and about Plotly also is that they provide abilities to interact in other ways, such as for example, hovering. So if I because all of the columns in this data frame and this column data source have names, I can create a set of hover tips, which are shown, which I printed out here, and then I can set up my figure to include among its tools a hover tool, and I can say, and I want the tooltips to be these set of fields in the column data source that I've identified. And now when I do that, I can hover over any point in this plot, and hopefully you can see this, and a box pops up, and it displays all the associated information for each point. And if I actually have at a point that's overlapped by two of these points, it'll plot multiple entries. But this is very useful, because even though I'm constrained in some sense visually to representing things in 2 dimensions, this is a higher dimensional data set, and I can I can use this kind of hovering capability to look at different aspects of the data in the same plot. And in fact, we've used the same kind of hovering technique in some of the training materials in our online Cornell virtual workshop, the CVW. So we have some plots that we're looking at sort of tweet and retweet timelines from Twitter data. And then I also have some stuff that is showing working with this baseball statistics data. So for example, I can go to this page that I've created separately. So this is now a static HTML page, where what essentially I've done is I've taken all of those hitting statistics for every player who's ever played, and I've used a t-SNE dimensionality reduction method to sort of embed that high dimensional data into a 2-dimensional plane. But now that I have that, I can go in and I can, for example, zoom in on parts of this plot. Every dot represents a person. The big dots represent people who are in the Hall of Fame. The blue dots represent people who are primarily pitchers and who typically then don't hit as well as the hitters. But this is a nice way to sort of navigate, the map of the history of baseball, and you can sort of see different trends popping out by looking at something like this. So it's a very useful technique and has lots of different kinds of applications. So that was all just sort of raw Bokeh, in the sense that I generated data, but because I was generating data that had additional HTML stuff embedded with it, additional data in the HTML, I was able to do things like hover, or there's other techniques that I didn't get a chance to show you. But Bokeh Server is a different kind of thing. This enables you to actually modify what gets displayed. So you can trigger new computations based on user interactions. And as I said before, this could either be run locally within a web browser where it's just kind of running on localhost, or it can be part of an accessible web server that's made public, on the internet. And this can be used to build big data dashboards or applications to allow people to analyze data. And the core element that gets added here is that we now end up writing callback functions that get triggered once we do various actions within the GUI, for example. So this can be used to just modify the display or to actually trigger new computations within the data. And so we typically are writing these callback functions in Python, even though then they end up impacting ultimately the JavaScript that gets displayed. And there are a number of different scenarios that I'll sort of walk you through here. So here's an example. This is from the Bokeh documentation. So this is one of the examples here, and you can see now if you look up at the top of the browser, I'm actually running. This is actually running on a server at demo.bokeh.org. So this is now a live server that's serving up this application. This is showing this same data, the same car data, the miles per gallon versus, in case of horsepower versus miles per gallon. But you can see on the left that there are these different selectors. So for example, if I wanted to plot the displacement versus the horsepower, I could just change that. Or if I wanted to plot displacement versus miles per gallon, I could plot that, and I could layer additional information using the color, the color and the size fields. So that's nice. In this case, based on my own interactions, I've changed what's being displayed, and this is basically all being coordinated through these callback functions. So I'm just going to take you very quickly to the Python code that generates that app on the Bokeh website. So there's a create figure function, and you can sort of see, this is sort of the main action here. It's using this circle method on the plot object to plot the X and the Y data and to plot the color and the size data. But then it also defines these select things. So it's so X, Y, size, and color are all instances of those select buttons that were showing up on the panel on the left. And what each of these say is that anytime something is changed in those select buttons, call this callback function called update. So anytime the value of what is in that select button changes, call update. And then update is this little function that basically just calls the create figure. So every time I change something in one of the select buttons, update gets called, create figure gets called, and I get a new, I get a new thing rendered. And that requires again, the Bokeh server. That's not something that would be embedded within a static plot necessarily. This is a screenshot of a much more elaborate example, something that I don't really have time to sort of show you in detail here live. But this is a web server that hosts multiple applications that I've developed in conjunction with Madhur Srivastava, who's in the chemistry and chemical biology department here at Cornell, and also is a member of the ACERT Biomedical Resource Center. So this is one of several applications running on this web server that we host here at CAC that's used for denoising ESR data, so electron spin resonance spectroscopy data. And this is an application that I built using Bokeh, so it's got multiple plot windows that are linked in various ways, and then it's got this whole control panel that is each of which, when I make some modification, I click on a button or I click on a radio or I change an entry in one of these boxes, that triggers one of these callback functions that goes back actually to the server. So users are running this on their individual browsers, but it's connecting to the server that's running at CAC. And every time one of these callback function gets done, something is recomputed. And in this case, what we're doing is we're taking this red input signal, which is kind of a noisy ESR data set, and we want to denoise it by zeroing out certain elements of components of a wavelet decomposition. So this is a method that Mater has developed and that we've implemented here, where using the graphical interface, we can selectively zero out different parts of the wavelet decomposition to generate then this black curve in the upper left-hand plot, which is less noisy than the original one. And these histograms on the right are representing the same data that's in the time series plots in the middle, and users can select thresholds based on either one of those things. And then when they're all done, they can download this denoise data. So in this case, users come to this website, they upload their data set, they do all the processing they want, and then they download it and they're done. And there's nothing that ever resides on the server other than while it's in memory while that browser session is open. But that's it's a very compelling way to sort of develop kind of centralized applications that people can access through the internet. So Plotly, I mentioned, is something that's kind of similar in spirit to Bokeh. It provides this kind of interactive visualization, and Dash is a separate but related package which implements sort of the server-based aspects of Plotly. So you can run Plotly by itself, or you can run a server using Dash, and then Plotly Express is a convenient interface to the Plotly plotting library. I'll note that Plotly has a lot more built-in analytics than Bokeh does. If you want to do contour plots, for example, in Bokeh, you would need to you would end up calling probably something from NumPy underneath to generate the contours, and then you'd have to figure out how to render that. Whereas Plotly has kind of more higher level built-in functionality, so that might be important for you. So, for example, I can run here. From my baseball data, I can say I want to make a scatter plot using the Plotly Express scatter method, and now, so one of the interesting things about Plotly is you sort of get the kind of the hover is kind of turned on automatically. Interestingly, here I can also compute a trend line. This is an ordinary least squares fit to this data, and I can hover over the trend line, and I can get the slope and the intercept for this line that it's fit to this data. So that's kind of nice. And I can also, for example, make a 3D scatter plot, which again is something that Bokeh I think does not support. But I can for example plot from the baseball data strikeouts and triples and home runs, and now I can spin this thing around in 3 dimensions, and maybe it's useful to have it in 3 dimensions, or maybe it's not. I can hover over any of these points and get information about it. I can even, apparently, I just discovered this the other day, I can click on a decade, so example, the 1980s, and I just get the subset of points for that decade. So depending on what you want to do, if you want to use this kind of interactive visualization, maybe even in multiple dimensions like this, Plotly might be a nice thing to look into. So that's the end of the bit on interactive data visualization. And I just wanted to say a little bit about a few other things. So one is 3D data, right? That I've been showing you a lot of line plots and scatter plots, and these might come from n-dimensional data sets, but I'm making kind of 2D plots. But often, in some instances, we want to make 3D volumetric renderings of something. I mean, typically of 3D objects. And so this would be, for example, something I might use if I'm looking at solid mechanics or materials or fluid dynamics or biomedical imaging. If I've got Z stacks of MRI slices and I want to reconstruct those into a 3-dimensional anatomy, then I might want something like this. So in some ways, this is an intrinsically more complicated type of data visualization that we have to, because now we're looking at things in 3D, we have to worry about opacities and transparencies to be able to see through the volume. We have to support sort of more complicated kinds of interactions like rotation and zooming and the like. Often we're representing complex 3-dimensional geometries for, say, some weird material or something, and we need to, we need to be able to capture that. And then often there's interest in sort of overlaying different kinds of data fields on those 3D geometries. and that needs to be coordinated. In 3 dimensions, we often have larger data volumes, so there's sort of processing power that needs to be thought about. And then there are typically more complex pipelines that are needed to organize all these different elements. And so I'm just going to talk a little bit about sort of one set of tools that I call the VTK tree. So VTK is the visualization toolkit, which is a library that's been around for several years. It's a large C++ library that represents, it's an object-oriented library that represents 3-dimensional objects and geometries and data sets that live on those geometries, as well as all the objects that you need in order to build up data visualizations. And one of the languages that it exposed to is that there's a Python API that lets you call VTK functions and create objects and methods on those objects. And so one scenario is that if you want to build up some 3-dimensional visualization, you can write Python code directly using this API to do so. In some ways, a more convenient thing is the ParaView package, which is built on top of VTK, which has a GUI that's written in Python, but that allows you to do a lot of the data loading and data preprocessing and building up, wiring together pipelines you can do graphically in kind of a visual framework. And you don't necessarily even need to write Python, although because ParaView is running a Python interpreter internally, you can in fact access parts of that. You can write scripts to automate parts of the pipeline. And some of this is described in a couple of topics in our CVW, one on ParaView and one on ParaView Advanced that Ben Trumbore has written. And then MyAV is another package that sort of sits on top of VTK and provides sort of useful functionality for doing various kinds of scientific data visualizations and 3D plotting. So I just want to show a couple of things these are things that I've made over the years using VTK, actually just using that low-level Python interface or the Python interface to craft these things. So on the left is an image that I generated a while back when I was working on kind of materials modeling, and we were interested in modeling material microstructure in polycrystalline materials and trying to understand how those materials deform and fracture under loads. And so all of the geometry represented here is something that is captured within VTK and rendered there. And the middle is sort of a schematic illustration of some work that I did in kind of biological information processing and trying to understand the structure of kind of high-dimensional sequence spaces that are used in signaling and regulation. And on the right is this animated GIF of an avalanche in a 3-dimensional magnetic material. So when you put a magnet in a magnetic field, it slowly magnetizes, but it does so in kind of fits and jumps. And so this is a single kind of avalanche triggered by one spin flipping and then that propagating through destabilizing the rest of its neighbors in this complicated fractal shape. And here we're actually using coloring to demonstrate the time evolution. So this particular avalanche started in the blues and then proceeded out through the greens and the yellows and eventually, you can through the pinks and the reds. And so you can convey temporal information with, for example, color as a cue to represent very complicated kinds of geometries. But you could do the same kind of stuff in ParaView. You would just have a different interface for generating that kind of data. So I've been focusing here on sort of general packages for creating different kinds of visualizations, and I think it's important to understand what those general packages do. But in some cases, you might be working in a specific area where you want to know if there's something more customized for your problem at hand. And so I did a little bit of work to sort of just try to see what. I mean, I don't use any of these things myself, but I wanted to see sort of what the landscape looked like, and this is a very incomplete list. But I tried to sort of identify some things that might be of use to people, to those of you at the med school working either in sort of molecular, biology or genomics and the like. So there are various packages for molecular visualization: PyMol, Py3D-Mol. And again, these are things that might use other technologies underneath, but they provide some kind of Python interface API for programming, some kind of data visualization. And then there are a number of things that are part of the scikits. So the scikits are this big collection of add-on packages for SciPy that are more tailored to more specific kinds of things, which is why they're not in SciPy. But there are a number of scikits, and scikits are not just about visualization; they're about all different kinds of data processing. And if you're if you're working in a particular area, you might want to try to look through the scikits. Unfortunately, the scikits page right now, which used to have a list of all the available scikits, that list is not working. But if you go to the Python package interface to PyPy, and you search for scikit packages with like a command like this, you can see a list there. And then there are various things that are tailored to specific application areas for doing spatial single cell analysis, or multi-dimensional image viewing, or sort of graph AI kinds of things, radiomics, a lot of kind of stuff associated with kind of medical imaging, or even kind of genetics, looking at genetic variation. So it might be that it's easier for you to just visualize what you need using the general packages like Matplotlib or Bokeh or something, or maybe it's easier for you to try to figure out how to use a package that's more domain specific that sort of supports what you need. So I'm kind of wrapping up here. There's some additional resources if you want to find out more. So we've had a few lectures in this series that are in this lecture series that are relevant. I gave a talk in the fall on introduction of Python. If you're still trying to come up to speed with the basics of the language, you could watch that. And then last month I gave a talk on Python for scientific computing and data science, which emphasized more the kind of the data processing side of the ecosystem rather than the visualization. And then, as I mentioned, Ben gave a talk recently on creating best visualizations for your data that you could look at. There's useful information on the Python website and on each of these kind of package websites. And then also within our CVW, we have a number of different topics related, in particular this kind of Python for data science, which incorporates visualization techniques alongside the rest of these kind of data processing things. So I have a few additional application examples which we can look at if there's time, although we're getting close and I want to leave time for questions. But in summary, I hope I've given you some sense as to what this Python ecosystem for data visualization looks like. Again, often what we want to do is we want to create figures for a paper or presentation, and there are a lot of great tools for creating those things. But as we start getting more complicated data sets that maybe we want to interact with in different ways, then these interactive data visualization tools and web server support tools can be extremely useful. If you are doing 3D volumetric rendering, you want to look into some of the packages, VTK, ParaView, what have you, that support that. And as I said, if there are more domain specific plotting functionalities you're looking for, you might try to hunt for those. So I hope I've given you some sense in which these data visualization tools sort of integrate with the rest of the ecosystem. That again, you might have a data file that you just want to make some plots from, and you might read that in with pandas and then use pandas plotting to generate plots, or you might be using NumPy and SciPy and a number of other things to generate data and through simulations and analyses, and then you would make calls to your to one of these packages, one or more of these packages to make some plots. So I'd like to thank you all for attending.